Yeah. Okay, today we will continue to focus on FT properties. Actually, you can see the FT properties will be very similar with FS properties. Yeah, and as we talk about the FT synthesis and analysis equations are very similar with the FS synthesis and analysis equation. Actually, why we spend so much time on FS, because FT and FS is very similar, but yeah, and let's continue. Today's goal, like first we will review the computation of the FT, and then we will talk about we will review the basic properties of the FT. Like actually we have already talked about those those three, yeah, but yeah, we didn't talk about yeah, I think we didn't talk about some examples. Yeah, today maybe we will talk about more examples. And then we will study the symmetry property of the FT. Actually, yeah, we know like the symmetric also, yeah, the FS also have a symmetric. Actually, it's very similar. And then we will try to use these properties to solve some problems. Yeah, similar with FS. Okay, let's try to review the FT computation. Yeah, if actually we know like if we want to compute the FT of a function, which means usually we talk about FT, which means FT like a coefficient. Yeah, we just try to short it like a FT. Yeah, and then actually usually if we talk about the periodic, we talk about FSM, right? But we want to just make 1, 2. So the FT we also can compute the FT for the periodic signal. Yeah, we have already talked about in last class. Yeah, for the periodic signal, what's the first step? If you want to compute the FT for a periodic function or signals, what you will do? What's the first step? Do you remember? Huh? 2 pi. Huh? 2 pi over t? Yeah. The omega, the fundamental frequency. Yeah, actually, yeah, that's right. But just a big idea, like compute the FS firstly. Yeah, compute the FS coefficient firstly, and then yeah, we know we can use this one, right? For choose the FS like coefficient. But usually we can use some properties to calculate the FS coefficient. Yeah, and then after that, you can see you can use if you can convert the FS to FT with this equation. Yeah, do you remember? Yeah, we talk about this. Yeah, and this is for the periodic signal, and for the non-periodic, like aperiodic signals or functions, like what you will do if you want to compute the FT of the function, what equation you will use? Yeah, actually, we will compute the FT by the definition, right? What's the equation's name? FT analysis. Yeah, this one. Yeah, and yeah, we know like these three. Actually, we have already talked about those three problems in the first class when we talk about FT. I don't know if you remember that. Yeah. We talk about if you're like signal is this one, and your like FT should be this one. If your signal is this one, and then your FT should be this one. Yeah, those three we will use it for today's lab. And do you remember what's the name for that? We talk about some too often used FT pairs. Yeah, this is those three too often used FT pairs. Yeah. Do you remember? Yeah, in the first class when we talk about the FT transform. Okay, and those three equations we will use later. And then just remember those three. Yeah, actually we talk about in the first class. And then let's talk about some common FT pairs. The other common FT pairs. Okay, if your xt equal delta t, what's your FT coefficient? Do you remember? Yeah, 1. That's right. And if your signal is 1, a constant, what's your FT coefficient? Huh? now it should be this one. Yeah, 2 pi delta omega. Yeah, you can see it's sort of like a corresponding. Yeah, you can see if you're like a signal is delta t and your ft is 1. If your signal is 1 and your ft is just kind of related to delta omega, yeah, it's just have the similar, yeah, if you want to remember it. If your signal is eg omega now t, and what's your ft? Do you remember? It should be 2 pi, yeah. Yeah, okay. And if your like xt is delta, like t minus t now, and what's your like ft? Yeah, it's kind of like opposite like that. Yeah. So if you want to remember it, yeah, you can remember like this, but it's unnecessary to remember it. Yeah, you can put it in your cheat sheet. Yeah, because when you resolve some real problem, yeah, you can always find these things. Yeah, online, very easy. Okay, and if your signal is the cosine omega naught t, what's your ft? Do you remember? Yeah, it should be pi multiple delta omega minus omega naught plus delta omega plus omega naught. Yeah, we talked about in the last class. Huh? Yeah. Kind of Euler. Yeah. And then if you draw this function, you will find you can get this one. Yeah. And how about the same? Yeah. Also, you use Euler equation, because you use Euler equation, you can change it to this kind of, and then you can see get this kind of like what? Yeah, like similar like this. Yeah. And then if you draw it, it's just kind of this form. Yeah. Okay. And let's review the other one. If your signal is this one, like xt equal delta blah blah blah. Yeah, and your signal is kind of like this. Like this is t. T, 2t, like 0, negative t, blah blah blah. Yeah. Do you remember we talked about in last class? And this kind of thing. And then we know like for the this is periodic signal, am I right? And the fs is 1 over t, fs coefficient. And then we can use to get the ft using this equation. Yeah, we talk about that, am I right? And then your like ft should equal this one. Yeah, any questions so far? Yeah, we talked about this in last class. Yeah, okay. And if you draw it, and it's similar like that. Yeah, it's just like this. Yeah, and then this is some common ft pairs. Do you know why we want to talk about those common ft pairs? Include those three. Do you know why? Yeah, similar with we talk about some common fs pairs. It can help us to find some complicated ft signals for of the ft coefficient like that. Yeah, and we combine with some properties. Yeah, and then let's review some the properties we talk about. Yeah, we talk about the linearity and the time shift. And the linearity, yeah, actually it's very similar with the linearity property we talk about in for fs coefficient. Yeah, which means if you have any signal, it's not only periodic signal, any signals, and the signal xt and the ft is x g omega, and for the other one, the other any signals, and you have the ft, this one. And then if you have a new signal, axt plus byt, what's the ft for the new signal? Huh? Yeah. ax j omega plus by j omega. Yeah. Actually, it's very similar with the linearity property for the fs coefficient. And the time shift actually is also similar. Yeah, this one, if your signal is it and your ft is x j omega, yeah, it's also equal this one. It's just like the magnitude and the phase representation. And then your new signal, xt minus t naught, which means this new signal's ft should like this. Yeah, if you put this one here, and then you can get this one. Yeah, that makes sense to you? Yeah, this is the time shift property. Yeah, any question? Okay. And then we talk about the frequency domain shift. Frequency domain shift, which means we don't change the time, we just change the frequency. Yeah, because we just multiple actual frequency to the original signal, right? And the new signals ft, yeah, we talk about, yeah, we just try to, yeah, because this is the ft for the xt, and we use this equation. And for this new one, and we just calculate using the analysis equation, and then you can see step by step. Yeah, compare this one and this one, you will find your new ft should be this one. That makes sense to you? Which means if you do a frequency domain shift in for this signal, for the ft coefficient, you also do a frequency domain. You also do a frequency shift. That makes sense to you? Yeah. Any question? Okay. And this, yeah. And then the new signals ft should this one. Okay. Yeah. We also call it modulation property. Yeah, it's the same property. Yeah, frequency domain shift property or modulation property. Yeah, actually, when we talk about the communication application, you will know why we call it modulation property. Okay, then let's talk about the other frequency domain shift. Since we know this one, and then for the cosine, if you multiple cosine signal for the original one, and then we talk about this in last class, and then we can use Euler equation to convert this equation to this form. And then you can see multiple this one here and this one here, and you can see you get the similar. You can use the time shift properties to get the new ft. That makes sense to you? Any question? Okay, and then sin, similar thing. Yeah, because sin you can also use Euler equation and to change and convert sin to this one, and then use the time shifting properties and get this one. That makes sense to you? Yeah, this is a new ft for this kind of signal. Okay, and then let's talk about some examples. Yeah, find the Fourier transform of signal for this signal, and then we know this is time shift property. I'm right. And this is frequency shift property, and yeah, and this is the three very often used ft pairs. Okay, based on this, first, how can you how can you resolve this problem? Can you see that? Yeah. Okay. How? Yeah, you can see this part. This one has two parts. I'm right. And let's resolve one by one. And for the first one, which property? Firstly, if you see this, which equation you will use? This one, right? Yeah, and then you can see there is a shift and this one. That makes sense to you? Yeah, so which means for this one, we can use you can first this one, and you can see firstly we can get this one, am I right? Yeah, because we need to get this one is, which means we just the a here is 3, am I right? So we can get this one, am I right? And then for this one, which means we need to do a shift, am I right? That makes sense to you? Yeah, then we can use this one. Yeah, for this we do a shift, and then which means we can use this one because multiple this part. The omega, the T naught should equal 2. Am I right? That makes sense to you? And then we get this one. So we have already resolved this part. And then let's see the other one. We just define this is xj omega. And then for this part, you can see this one equal this one. That makes sense to you? Because using Euler equations, just change this one to this one. That makes sense to you? Yeah, and then which properties you will use? Yeah, actually, you don't need to calculate it. You can see, you just multiply this one with this one. Yeah, this one actually is a fixed kind of constant number, am I right? You don't need to man this one. You can see you multiply these two and multiply these two. Yeah, which property you can use for this part? Yeah, you can see here. Am I right? Here, the omega now should equal 2. And then, does it make sense to you? Does it make sense to you? Yeah, then you can get this one. Yeah, this part should equal this one. Yeah, because the omega now here is 2. And this one, this part of the FT is just this one, this one, am I right? That makes sense to you? Any question? Any question? Yeah, let me explain. Yeah, you can see for these parts, the FT is this one, am I right? That makes sense to you? Yeah, this is just the whole thing is just the xt here. That makes sense to you? And then you multiply this part, it's just kind of this part. The omega now is 2. And then you get this one. Yeah, because you have this one. Any question for now? No. Yeah, okay. And then you can see for the whole part, you get the FT, so this one. That makes sense to you? And then let's try to, because this one equal this one, and this one equal this one. Yeah, just put this. That makes sense to you? Yeah, and then try to simplify that, and you will get this one. Yeah, because you just put 2G inside, 2G inside. Yeah. Then you can get this one. That makes sense to you? Yeah. Okay, any question? Yeah, so yeah, which means if you want to calculate the FT properties, FT like coefficient for some complicated signals, usually you just you don't need to use the analysis equation step by step. You just use some like very often use the FT pairs and some properties. You can easily to get the final result. That makes sense to you? Okay, let's see the other one. This one. Okay, for this one, let's try to yeah. We know like this like a frequency domain shift property. And for this one, yeah, you can see this one, we can put we can convert this one to this one. That makes sense to you? Yeah. Any question? Yeah. What equation we use here? Eh? we change this to this. What properties what equations we use? What equation? What's the difference between this one and this one? We just change this part, am I right? Yeah. What's the equation? Euler equation, am I right? Yeah, you just, yeah. And then for this one, you can see you just put this one here. You can get this one, am I right? And for this one, you can see here, you know this one. Huh? Yeah, this equation is just too often like several often used. Yeah, which means you have the like FT for this part, and then this part, yeah, it's similar with this equation. Similar with this one. It just do a frequency domain shift. Yeah, which means you can. Yeah, this is just like a. Yeah, you will get this one. Yeah, because this one is just a dual phase shift, this one, and this is dual phase shift, this one. That makes sense to you? Frequency domain shift. Yeah, using this equation. Any question? No? Okay. Yeah. Okay. Then let's talk about one new property. Before we talk about one new property, let's review one property for the FS coefficient. Yeah, like the symmetric properties. Yeah, we know like if you have a signal, periodic signal xt, and your s coefficient is ak, which means if your like x star t, the fs coefficient should be this one, and then your like negative t, the inverse will have fs coefficient, this one. Yeah, this is the symmetric properties we learn in fs coefficient. And then for the real signal, and the AK should have this property, and we call it a conjugate symmetric. And then you can see if we have let's try to review. If you have this properties, if you have this fs properties, yeah, and for the first one, like what does it mean? What does it mean? Yeah, if A1, this one, and the A negative one is this form, which means what? Which means what? Do you know? Yeah, which means AK should equal A, yeah, is equal A negative K conjugate. Am I right? Yeah, which means this signal is real signal. Yeah, that makes sense to you? Yeah, any question? Yeah, you can see the you know, like if I just write A1, A negative 1, which means others are all 0, am I right? You know that, am I right? Yeah, which means if my if my A k equal 1 plus G, A negative k equal 1 J K. And then you can see A negative K conjugate, which means you just flip this symbol, am I right? Yeah, those two equal with each other. So if you have this one, which means you have a real signal. Yeah, and for this one, I think this one is a sim. How about this one? BK and yeah, you can see the BK equal B negative K conjugate. It is a real signal. How about this one? Which means what? Huh? Are you sure? Yeah. At least we know like the. Oh yeah. This is BK also equal negative B negative K. Yeah. And what does that mean? If you have this one, what does that mean? Which means your function is odd. Yeah. And then for the C, yeah, you can see your CK equals C negative. Yeah. Yeah, you are right. It's real. Yeah. And then actually your CK equals C negative K, am I right? Which means it is what? Even, yeah. And for this one, yeah. Yeah, because DK doesn't equal D negative K conjugate, which means it's complex, am I right? And then, yeah, DK equal D negative K, which means it is even, am I right? So it is even but complex, yeah. And for this one, yeah, which means it is the EK doesn't equal E negative K conjugate, yeah, which means it's complex. But EK equal negative E negative K, which means it's odd, am I right? Yeah, so this is Fs coefficient, like a symmetric property for the Fs coefficient. Actually, for the Ft, it is very similar. Yeah, you can see. And first, let's talk about the conjugation and the time reversal. If you have a signal, xt, and a signal, and the Ft coefficient is this one, and then your conjugate, what's that? Do you know? Yeah, actually, is this one. Yeah, and negative x negative t will be this one. Yeah, you can see you compare this one and this one. You can see it's very similar. Yeah, and then for a real function, which means xt equal x negative t, which means those two should equal with each other. Am I right? Yeah, because this one equal this one. That makes sense to you? Yeah, and if you're like we call it conjugate symmetric. Yeah, also you can write down like this. Yeah, because you can see conjugate here, also conjugate here. It's same thing. Yeah, and then which means for the real part, if you have this one, the real part will equal this one. The imaginary, which means it is even. Am I right? And if you have this one, if you have this one, and which means this one is odd. Yeah, that makes sense to you? Yeah, it's very similar with the Fs coefficient. Yeah, any question so far? Okay, and then let's talk about for real function. Yeah, we know like this equation. I mean, for real function, the ft should equal x conjugate t like that. Am I right? And then for this one, the magnitude is it can be calculated in this equation. Am I right? And then for this one, and the magnitude can be also calculated in this equation. Am I right? And which means those two should be equal with each other. Am I right? This one should equal this one. That makes sense to you? And then this one, you can see if this one equal this one, which means it is even. Yeah. And then for the freeze, you can calculate the freeze using this equation. Also calculate the freeze using this equation. You can see it is equal negative. Yeah, this one. Actually, it will be odd, which means for a real function, and your magnitude will be even, and your freeze should be odd function. Yeah, we talked about this in previous class, but this is just try to prove why. That makes sense to you? Any question so far? Okay, and then yeah, we also talk about this for previous magnitude spectra for different filters. You can see this one, yeah, because we have different filters. Yeah, for this one, what's the kind of the first one is kind of what kind of filter? Yeah, low pass. Yeah, and also this is low pass, and this is band pass. But we talk about usually we just use the opposite positive part. Yeah, we just use this one. Yeah, if you use this one, you can see it's like a common figure we usually use. Yeah, we just use because this one can help us to pass a low frequency signal, and this is can help us to pass a high frequency signal, and this is just help us to pass a band like this range frequency signal, and this is just help us to remove this part signal. That makes sense to you? Yeah. Okay. Do you know why? Do you know why it will help us to remove? Do you know why? You know why? Yeah, why this kind of like a thing? If we just have this, if your like magnitude, ft magnitude, have this form, and you will have a low pass filter. Do you know why? Yeah. Come to the definition. You can see. Okay. Yeah. You always remember like let me open it for you. I'm afraid you just forgot that. Oh, this one. Okay. Yeah, this one. You can see. Yeah, this is a frequency. This is a signal, like a definition. Am I right? And what's this? This is what? This is just the magnitude we talk about. Am I right? Like the ft we talk about, which means this is the coefficient for a specific like a frequency. Am I right? What does frequency mean? And what does coefficient mean? Which means, you have a signal. You have this signal. Am I right? And if your signals have this frequency, this is omega y, omega 1, omega 2, omega 3, right? This is your frequency representation. If your like x j omega 1 have 1, which means you just try to keep it, right? If your x j omega 2 is 0, which means you will remove that. Am I right? That's the reason why here, because you can see it's just kind of a coefficient. If this coefficient that is now 0, which means you keep it. If the coefficient is 0, which means you remove it. That makes sense to you? Yeah, that's a reason here. Like okay, no, this one. Yeah. Okay, let's continue. Yeah. Yeah, that's the reason why if our like coefficient is like this, because you can see 0, which means we multiple 0, am I right? In this kind of to apply to this kind of frequency, am I right? Which means we will remove that. And if it's now 0, which means it has some value. After we multiply it, it will keep that. That makes sense to you? Yeah, any question so far? Okay. And then let's continue to talk about symmetric property. Okay, for the symmetric property, like for the FS property, symmetric property for the real like signals, we know like any like signals can be represented by this form, the even part plus odd part. We know that, and for the like the real part, the FS coefficient will be the real part of AK, and the odd part of like sorry, this is even. The even part of the like signal, the FS coefficient will be the real part of AK, and the odd part of the signal, and the FS coefficient will be the imaginary part of AK. Yeah, we talk about that when we learn the FS coefficient. Am I right? Yeah, do you remember? Yeah, and similar for the like FT. Yeah, a real function can have even order decomposition. Yeah, this is the true thing. Am I right? We learned this. Any signal can be represented in even part and odd part. Am I right? Yeah, we know that. Am I right? Yeah, and then actually for the real part signal and the FT should equal like we know that if it is a real signal, we have this equation. And then the order, the inverse xt will have this ft. Yeah, we just talked about that. And which means for the even part, yeah, you can see you have the real part like ft, and for the even part, for the odd part, you have the imaginary part of ft. Yeah, you can see compare with this one and this one, it's similar. Am I right? Yeah, for the even part of your signal, and you have the real part of ft, and for the odd part of your signal, and you have the imaginary part of your ft. Yeah, it's similar. Any question so far? No? Okay. Yeah, so which means the real and the even signals will have the real and even ft, and the real and odd signals will have the imaginary and the odd ft. Yeah. Okay. And then this is system symmetric property, like a signal, like symmetric properties. Okay, and let's try to review some questions. Yeah, so this is some signal, right? And yeah, these signals, this is kind of 3 different signals, and this is some like properties, and the real part of the like xg is 0, and the imaginary part blah blah blah. Yeah, it's some properties here, and like this is just from our textbook. Yeah, and let's try to review some questions. Yeah, which signal is real and odd? You know, which signal is real and odd? Yeah, for this, there are 3 different signals. Which signal is real and odd? Hmm? Yeah, the first one, right? Yeah. Yeah. 对的，没上去。Yeah. Why do you laugh? Yeah. Okay. And which signal is real and even? Are you sure? Yeah, actually, this one is just this kind of signal. It will not like this. It will continue, but this one is not continuous. Huh? None of them. Yeah, you're right. None of them. Yeah. So which signal can be shifted to be real or even? Huh? Well, you just the first one, I'm right? Yeah, that's right. Yeah, the first one, if you can see, if you shift it to here, it will be the odd, the even. Yeah, here it is odd, am I right? Yeah, and how about the other one? This one it can be shifted to even odd. No, am I right? Yeah. How about this one? Yeah, actually, you can see if you shift this one, you can. that没上去? Yeah, you can see, you can shift it like this, and then it will be odd. that没上去? Yeah. So, yeah, the A, let's try to, it is A, and this is B. Yeah, and then, yeah, let's have this one. Okay. Which signal has x0 equals 0? X0 equals 0. Yeah, you're right. Yeah, I think this one is a tricky one, am I right? And then, which signal is discrete? Huh? Yeah, B, am I right? Oh, yeah, there is a B, sorry. I just, okay. Yeah, this one should be the discrete one. Yeah, and then, which signal is periodic? Yeah, the A, am I right? That's right. And which signal is the zero average? Yeah, A. Yeah, you're right. How about B? No, not B. Sorry. I just how about C? Yeah. How about C? Huh?
Well, there's only on the right side.
But the zero average, which means the value. Yeah, what's the value for this part? What's the value for this point? It will be this one. What's the value for this point? It will be this one. Yeah. So you can see, you can easily see this question, this signals, try to decide which signal is real and odd, which signal is real and even, blah blah blah, based on the image, right? But you can also tell which signal is real and even based on the properties. Yeah, based on this one. If your real part is 0, what does that mean? If your real, yeah, we know let me show you. Yeah, which means this will real 0. Am I right? Which means there is no even part. Am I right? Which means this signal is odd. That makes sense to you? Yeah, similar like that. If your imaginary part is 0, which means this one is 0, am I right? Which means you don't have odd part, which means your signal is even. That makes sense to you? Yeah, any question? Yeah, actually similar like this. And if there exists a real A such as blah 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 is real, yeah, which means you can have some properties. Let me show you. Yeah, e.g. okay. Yeah, this is do you know what properties we will use? Do you know? This one. Shift property. Am I right? Which means if you have your that this one is real, and then which means which means you have some other the properties you can use and to see if this signal is real or odd. if it is like a real, if it is real or if it is odd, if it is even or if it is complex, if it can be shifted. Yeah, you can also use some properties to decide if it is like real and even. Yeah, that makes sense to you? Yeah. Yeah, I will leave this to you to the homework. Yeah, actually, this is a homework. And I just want to tell you, like, you can use some, after you draw these figures, you can tell some properties. But also, you can use some, like, properties we use, yeah, to figure out how, what kind of signals it is. Yeah, this is for the, like, symmetric properties. Usually, you will use symmetric property, linearity property, and FT property to decide. Yeah, that makes sense to you? Okay, any questions so far? Yeah, this is the homework for today. Like, yeah, this is just the properties we talk about today, and to resolve those kind of problem. And we will talk about the left property, uh, this one, the integration and the differentiation. Do you remember for the FS properties, we talk about the linearity, the time shift, symmetric, and linear, like integrating and differentiation, and yeah. For the FT, it's a similar thing. Yeah, we will also talk about the integration and the differentiation. Yeah, and you will find that it's very, very similar. Yeah, and then let me ask you again this question: why we learn some properties? Because what? Yeah, now because they are similar, we learn that. Yeah, there is the purpose why we learn the property. Yeah, because it can help us, you can see. Yeah, it can help us to find the FT property, FT coefficient. Yeah, and we don't need to use the analysis and the synthesis equations. You can see if you use the synthesis equation, it will be very complicated for you. Yeah, but if you learn some properties and you learn some like common used FT pairs, you will find it's very easy for you to compute the FT coefficient. You can see for the midterm 3. Yeah, actually, you can see you don't need to use the synthesis and analysis equations. You just focus on the properties. It will be very easy for you to compute the like FS coefficient. That makes sense to you? Yeah, the properties are very important. Okay, yeah, this is today's class. Any questions so far? Okay, yeah, and the next class will be the last class for the chapter 4. Yeah, we will finish the FT transform. Like I said, let I talk with you. Actually, when you learn some other classes, you might never heard FS coefficient, FS thing. But you must heard FT, transfer Fourier transform. Yeah, what's the difference between FS and FT? Let me ask you again. Yeah, one is period, the other is for all signals. Yeah, FT, we know like it also can be used for the periodic signal, am I right? So when we deal with signals, we will never talk about FS because FT can be used for any kind of signals. That's the reason why we usually talk about the FT. But why we spend much time on the FS, now FT? You will find, yeah, why? Yeah, it's easier for us to understand because you can see the periodic signals for the the FS is quite easier to understand. You can see the periodic signals is just a limited number of like component. Am I right? So you use some summation, and you can see for many examples, you just find A2, A-2, A1, A-1, A0, maybe A3, A4, but not like A10, A100. Yeah, it's very like weird. But for the non-periodic signal, yeah, you can see you need to like go through all the frequency. Yeah, that's a big difference because FS is very easy for us, not very easy, quite easy for us to understand. After we learn the FS and FT is easier for you to understand. Yeah, but you can see the FS and the FT actually is very similar. Yeah, just have the similar theory thinking. Yeah, theory ideas. Yeah, so that's the reason why we just focus on FS for a long time. Yeah, because after you learn the FS very well, you will find that the FT is easier for you. Yeah, I don't know if you have this feeling. Yeah, actually, yeah. Okay, this is the class we learned for today. Yeah, just remember those properties, and we will finish the chapter 4 next class. And for the next week, we will review all we learned, and also some communication and sampling. Yeah, I will talk about a little because those two are the applications for signals and the system. It's very important, but you can see it's just use the theory we talk about like so far. Yeah. Any questions? Okay, yeah, that's great. Okay, and yeah, there is new homework today. Okay.